The humble two-way loudspeaker, the workhorse of the industry. They've been around since the 1920s, and they're found pretty much any place that has a sound system. There's hundreds of them on the market, ranging in size from a 4 or a 5 and a tweet to a 15 and a horn. And the prices range anywhere from dirt cheap to, are you kidding me? So once you've narrowed down your selection to the frequency response and output and pattern that you need, how do you make the final choice? How do you decide which loudspeaker is the best? What is it that makes a truly great loudspeaker different from the others? Now, any great quality product has to start with great products, excellent craftsmen, and great construction techniques. Here at EAW, that starts with the void-free birch plywood that we get from Russia. And the craftsmen that we have at our factory here in Whitensville, Massachusetts are some of the best in the world. The result is an incredibly well-built, durable product. Now, the other thing you need to build a great loudspeaker are great transducers, and we search the world for the best transducers for our products. Now, we check them out, we test them, we torture test them, we listen to them, and we're not just looking for the best transducer, but we're looking for the best transducer for the application. So how many transducers do we check out? Well, a lot. Well, good quality materials, construction techniques, and transducers are probably all you need as long as your audience is pretty much lined up right on axis with the loudspeaker. But what about these folks sitting out at the edge of the intended coverage area? Are they getting the same listening experience as the ones who are sitting right on axis? Now, this is what really separates the truly great loudspeaker from all the others out there on the market. This idea of spatial consistency across the entire intended coverage pattern, that listeners that are sitting off axis get the same listening experience as those sitting on axis, either horizontal or vertical. Now, they say a picture is worth 1,000 words, and measurements can give us some very interesting pictures of the performance of a loudspeaker. Right now I'm doing a measurement called a spectrograph. What we're seeing here in the vertical is the frequency from 100 hertz to 15,000 hertz. Horizontally, we're seeing a moving time window of about 25 seconds of time. And then levels are indicated with color. So I can see what's happening over time across the entire frequency band of the measurement. So if I take a loudspeaker and put it on a turntable, and then put a measurement mic out in front, and then play pink noise through the loudspeaker and slowly rotate it while I'm taking this measurement, we actually get a pretty good indication of the polar performance of any given loudspeaker we're measuring. So let's try that with a typical two-way loudspeaker. So here's our measurement, and I think you can see there's quite a bit of information here, but I want to focus on the polar characteristics. Let me just note that these measurements are taken in less than ideal conditions, so some of these little peaks and ripples and valleys are actually caused by EQ problems and reflections and whatnot. The first thing we note is that down at these low frequencies, this loudspeaker is pretty much omnidirectional. Well, that's to be expected with a loudspeaker of this size, since these wavelengths are much larger than the loudspeaker itself. The low frequency starts to show some directionality around 250 to 300 hertz and becomes more narrow as we get higher in frequency. Then we get to the crossover point around 2200 hertz where it flares back out again and stays fairly consistent from there on up. Now we're directly on axis right about this point, and then these marks out to the side would be 90 degrees off axis from one side to the other. This would put our 45 degree off axis marks around this location, and we can see that this loudspeaker is somewhere around 80 to 90 degrees horizontal coverage. The problem here is that anyone who's sitting in the edge of the intended coverage area here and here would have a giant hole in the response right around that 2000 hertz range, and this also happens to be the most critical band for speech intelligibility. And this problem gets even worse when we look at the vertical polar pattern, but any loudspeaker with physically separated sources will have this problem to some degree or another. But we'll talk about that in another video. Along this hallowed hall is the heart and soul of EAW. Kenton Forsyth down that way, the president of EAW at the end, the engineering department, and one slightly OCD marketing director. This is where the acoustical, mechanical, software engineers, astrophysicists, and other geniuses are hard at work developing the future of EAW. Well, a few years ago, they were considering this problem of maintaining beam width through the crossover. One of them said, well, hey, let's just make the horn about the same size as the low frequency, both horizontal and vertical, and then we'll set the crossover point where the two have about the same beam width. Well, it was a milestone in human history. Well, in pro audio history anyway. It was the birth of EAW's core technology, beam width matched crossovers. Now this is the MK2396. This particular one happens to be our engineering reference box. First thing you notice is that the horn is quite large. In fact, it's about the same size as the 12-inch low frequency. This means it's able to maintain consistent pattern through the crossover point into the low frequency device. Secondly, you notice that the horn is square, that it's the same size horizontal and vertical. This means we maintain that beam width control vertically as well as horizontally. So let's take a measurement of this one and see how it compares. Well, I think the advantages of beam width matched crossovers in this loudspeaker are quite clear in this measurement. The crossover point for this particular model is around 1200 hertz. The low frequency locks into the pattern at around the 600 hertz range, and beam width is maintained from there through the crossover point into the high frequency. And we compare that to our previous measurement, and I think we have a winner. Well, I hope this gives you a better idea of just how innovative engineering can help even the lowly two-way loudspeaker. Beam width matched crossovers can be found in many of our products, including the classic MK series and our new VFR series. If you'd like more information on the fundamental physics behind beam width matched crossovers and other EAW technologies, then be sure to visit the support section of our website. I'll see you in the next video, and until then, I wish you consistent beam width.